Hello everyone, welcome to this presentation on real-time operating systems. My name is Isaac Greaves and I'm going to be presenting with Corey Dan and Dan Rayberg. So what is going to be in this presentation? First of all, we're going to talk about real-time operating systems versus your conventional operating system. Conventional operating system meaning something you would probably see in your personal computer. The next thing we're going to talk about is examples of real-time operating system applications, where you're going to see them in your day-to-day life. Next thing we're going to talk about is safety and security. What about operating systems makes it so that we need safety and operational security of operating systems? Next thing we're going to talk about is intersections with mainstream OSs and real-time operating systems, where regular operating systems and real-time operating systems become compatible with each other. The next thing we're going to talk about is the future of RTOSs and what the trends are going. Alright, real-time operating systems versus conventional operating systems. Real-time operating systems are different from conventional operating systems because they have real-time constraints. They have a certain amount of time to finish a function before there's operational failure. There's 3 types of real-time operating systems. First of all, there's hard, firm, and soft. Hard means that every single function and every single process has to be successful in the time constraints or there will be system failure. Firm is the next level where some processes can be starved and fail and there's still operational success. The next thing there is soft real-time operating systems, and this is where many processes can be starved out and there can still be operational success. Real-time operating systems can also run in kernel mode, and they may also remove dynamic memory allocation for time costs and to avoid fatal memory leaks, which can cause operational failure. Next thing we're going to talk about is the applications of real-time operating systems with respect to QNX Neutrino. This was developed since the 80s, and they pioneered modular architecture. This is where there's brick wall partitioning, where certain processes or functions of one module system have their own assets, their own data, so that one function is separated from another function. So if one function fails, it doesn't affect the other function. Think about your car, for example. If your brakes fail, you don't want that to affect the operational success of your airbags, because that would risk your life. So we want to make sure that even if your brakes fail, your airbags will also succeed. And I'm going to leave it off to Corey.
I'm Corey, and I'll be talking about a few of those applications. So Texas Instruments is well known for their calculators. Their more complex calculators use a real-time operating system known as RTOS. It provides Internet of Things support, and that allows the calculators to exchange data over Wi-Fi or Bluetooth. This data exchange is made quick with its universal asynchronous receiver transmitter and inter-integrated circuit APIs, which allow the data to be read from memory in parallel, the bits transmitted serially, then reassembled in parallel. Real-time operating systems are also used in all kinds of medical devices. One such operating system is MQX RTOS, which also provides various Internet of Things protocols. It was designed for embedded systems, which were assumed not to have as many resources as a conventional system would have. Its context switching was optimized around these limitations, which resulted in a 0.551 microsecond context switch time and a 0.331 microsecond interrupt latency. What's more, unlike many RTOSs that only support C and C++, MQX RTOS also supports Java and Object Pascal. Another real-time operating system is Integrity RTOS, which has protocol support and applications similar to those of MQX RTOS. But where this differs is in its security focus. Not only does it encrypt transmissions with WPA2, but it's structured in a way to limit data leakage, which of course is important for patient privacy. Its partitions are separated from the kernel instead using a localized kernel API, thereby protecting not only other partitions from a compromised partition, but the kernel itself as well.
Real-time operating systems also have their own issues regarding safety and security. While there are many topics that could cover safety and security, one of the ones to focus on would be the modularity design of the system for which a real-time operating system is running on. Some real-time systems have separate physical modules. In the event that one module fails, the entire system doesn't necessarily have to fail. An example of this might be in proximity detection in a motor vehicle for the potential of a side-swiping incident. If that fails, the entire car and network of embedded systems communicating together doesn't necessarily have to fail. However, there are situations where you can't have a bunch of physical modules within one larger network. So the idea of brick wall partitioning comes in, where you have a series of different systems all working off of the same real-time operating system. But the function for each of those systems should not interfere with each other. So you need strict time scheduling and a means of ensuring that one function from one system is not going to break the integrity of another system. There's also the potential to have several microcontrollers within a single device. Such a system can check if a bad value was given or an incomplete value, something that would cause the system to fail, and that can be redirected to a microcontroller dealing with safety to correct that value and allow the system to be restored without a critical failure. There's also a concern between flexibility and reliability with real-time operating systems. Real-time operating systems have constraints that general-purpose operating systems do not face. This strictness means you can't just port or extend the use of existing software verbatim. You might have to repurpose existing software, but the real-time operating system still at least assists in the development process of software for a given situation. Something that is important though, and very similar to other aspects in the software world, including with general purpose operating systems, is a need to be able to correct any bugs and issues within a deployed real-time device. This could be as simple as providing some type of security fix to an Internet of Things device, or transmitting new software to a different planet for a deployed rover or helicopter. The growth in real-time operating systems and real-time systems in general directly relates to the increased manufacturing of embedded systems, which seems to correlate with general-purpose operating systems transitioning to these embedded devices. In order to have a multitude of software for a single general-purpose operating system, work between different microarchitectures, you need to translate native code from one instruction set architecture to another. In the case of Apple moving to their own in-house ARM chipset, they've opted for preprocessed binary translation. Similarly, Android has moved away from converting bytecode at runtime using the Java virtual machine to preprocessed binary translation for the Android runtime, in which the software is just stored as native code. More interesting is dynamic code translation, which Microsoft has extended the use of Windows on Windows 64 for intercepting and translating x86 or x64 instructions to an ARM chipset. Previously, it was used for converting the 32 bits of x86 to 64-bit word lengths for x64. Microsoft has also started actually delving into developing real-time operating systems. And this is assisted, I think, a little bit with the development with the augmented reality product line called the HoloLens, for which you need real-time responses to ensure that human interaction is not going to be too disjoint, either temporally or spatially, with what's augmented in the user's environment. For real-time devices, the Internet of Things has been a massively booming market, with an estimated tens of millions of IoT devices currently out in the wild. Although always look at the estimates and projections with a grain of salt. Despite the boom in the Internet of Things, there's a lot of useful microprocessors in use for real-time systems outside of the consumer market space. These include within the military, within the medical sector, and even with space exploration. While there have existed autonomous vehicles in the past, typically in the aerospace sector, more consumer vehicles are likely to emerge that have autonomous capabilities that will require strict time-constrained real-time responsiveness to ensure the safety of the passengers and pedestrians involved. There's also the possibility of a large growth in the augmented device space. Specifically, it could be useful for industrial work and training, in which someone could overlay a heads-up display or see what the trainee is seeing in real time to help direct them through their actions and activities. There's also just general productivity in the office space and trying to do collaborative work remotely. And then there's just general commercial products that could exist with people walking around and getting information about features they're seeing in their environment.